Okay, so it is exactly 4 o'clock. So I guess it is time to start. My name is Panos. I'm the Photonics Technologies Program Manager in EPIC. And today I'm pleased to be here with you to present these new products. So actually today we have 5 new products from EPIC members. We have one from Oxford Lasers, from Ibsen Photonics, neoLASE, QiOVA, and Biomimetic. But before entering more details in those products, I would like to say a few things about us and about EPIC. So we are the European Photonics Industry Consortium, and we are the world-leading industry association that promotes the sustainable development of organizations working in the field of photonics in Europe. And we now count for more than 700 members. Basically, as for today, we are 781 members, and we keep growing. The areas that EPIC is active are many and varied. We're organizing technical workshops and roundtables. We serve and sustain a highly valuable network. We help you with market intelligence and with the support of Tracy Vanik. And we help you also raise capital. And we support HR activities with the biggest website to find a job in photonics. In this slide here, you can see all the people behind this great effort of EPIC. And now let me pass to our today's topic and speak about those 5 fantastic people that are presenting today. Our first speaker will be Thomas Rasmussen, the Director of Product Management at Ibsen Photonics. He will be speaking about their ultra-compact pebble near-infrared spectrometer. Such a spectrometer is a game changer as it is both ultra-compact and more cost-efficient than the traditional spectrometers for near-infrared. The pebble near spectrometer is in addition to the pebble platform of Ibsen's ultra-compact spectrometers with a form factor of only 23 times 21 times 8 millimeters, high resolution and sensitivity, as well as environmental ruggedness. We will continue with Maik Frede, the founder and CEO of neoLASE in Hanover, and he will be speaking about their smart ultra-short pulse laser, which actually is a combination of pico and femtosecond laser pulses within one compact laser system. The alliance is based on highly reliable and low maintenance fiber oscillators and robust solid-state amplifiers. The new developed laser system further expands the neoMOS pulse duration range into the area of less than 100 femtoseconds up to a few 10 picoseconds or even nanoseconds. This system represents a universal tool for several machining processes such as drilling, cutting, structuring, and ablating. And pulse energies of up to 500 microjoules and average output powers of up to 100 watts are possible, opening, of course, a wide field of laser applications. We will continue with Melvyn, the Micromachining Sales Director at Oxford Lasers, who is going to present their new ultra-fast laser added to Oxford Lasers Contract Services Department, increasing the range of jobs that they support with welding of glasses to metals, thin film removal, patterning, and transparent material cutting and milling. Then we will go to Emmanuel Stratakis, the CEO in Biomimetic from Crete in Greece. He will present the Thetix anti-reflective and anti-fogging ceramic coatings and their laser systems for anti-reflection and anti-fogging ceramic treatment. And finally, we will have Florent Thibault, the CEO of QiOVA. He will be speaking about the multi-beam laser marking solution. He will be presenting their new multi-beam marking system that finds application in anti-counterfeiting, fraud protection, tracking and tracing along the supply chain. This product promises to combine the requested precision through output and quality. And the 2D data matrix of alphanumeric are stamped in a single laser pulse at a rate exceeding 10 unique markings per second, down to a few of 100 micrometer size. Please remember that we're also live streaming on YouTube, and the ones in the room are encouraged to ask any questions that you might have in the chat or raise a hand, and also the ones that follow on YouTube can also ask questions, and I will bring them in the room. And it's time now to pass to our first speaker, Thomas Rasmussen, the Director of Product Management at Ibsen Photonics and their ultra-compact near spectrometer. So I will stop sharing my screen. Thomas, whenever you're ready.
Thank you very much. So I'll be sharing my screen now. I hope you can all see it. Yeah, so thank you very much for the introduction. As mentioned, my name is Thomas Rasmussen. I'm responsible for product management here at Ibsen Photonics. And today I'm going to present you a new product that we made, an ultra-compact near-infrared spectrometer, and also talk a little bit about some of the applications that we see for this spectrometer. Before I get too deep into that, let me just spend 2 slides explaining who we are as a company. You may not know Ibsen Photonics, but we are a manufacturer of OEM spectrometers, and our customers are typically instrument manufacturers that build instruments for spectroscopy. Our core technology in the company is actually making fused silica transmission gratings, and we produce more than 40,000 of those every year, also for lasers and other applications. And some of the benefits of this product is that it has high efficiency, good stability, and enables us to make very compact designs due to a high groove density of our gratings. We also have a spectrometer design team in-house that actually combines or completes more than 6 projects every year. So they have a lot of experience, and some of the things that they are able to do customize for different customers is to make environmentally robust, stable designs that are well suited for mass production. And then finally, of course, we have our spectrometer production, where last year we produced more than 8,500 spectrometers for various customers. And again, some of the key benefits that we bring to the table is a low unit-to-unit variation by the design, which actually enables our customers to have good transferability from instrument to instrument. We'll come back to that later on. Also, just to very quickly show you, we basically cover the range from 175 nanometers up to 2.5 microns in the near infrared. And we have a range of different product platforms, but today we're going to talk about Pebble down here, where, as you just mentioned, we have a visible NIR version of Pebble, but now we've added also into the near infrared by a near infrared version of Pebble. So that's what we're going to talk about today. So here's a product. You see a picture to the right, and the wavelength range is fairly standard, I think, for a near spectrometer, 950 to 1700 nanometers. One thing that's a little bit better than most of our competition is that we have a 0.2 NA numerical aperture, or if you like, a F number of 2.2. So that means we actually collect a lot of light from the sample. Also, the resolution around 12 nanometer is pretty good for such a small spectrometer here. We're using an uncooled in-gas detector with 128 pixels. That's one of the reasons why we can get this into such a small unit. And the footprint is, roughly 2 by 2 centimeters. And one of the benefits also of this kind of diode array spectrometers is you can get really high frame rates. So if you're measuring on things that move, or like on a conveyor belt or something like that, well, then you can basically get a spectrum or 3000 spectra every second. So as we see it, some of the benefits of this product is, of course, first of all, its compact size. If you're building something that needs needs to be small or handheld, low weight, well, this is obviously a good choice. Even though that it's so small, it actually has high sensitivity. And as you just saw, it has a high frame rate. So again, if you need something that can record a lot of spectra per second, this could be the way to go. And then the final 2 things is that even though it's such a small compact spectrometer, it actually has quite high environmental stability against vibration and temperature variations. And it also offers a low unit-to-unit variation. So let's look at why we chose to focus on that. So one of the key applications for near-infrared spectroscopy is the process industry. So typically, this is not a lab type instrument, but it's something that has to work inside a factory or on the factory floor even. So for that reason, there are 2 key things that are important. One is that the instruments are stable, and the other one is because you're probably going to measure on a lot of instruments that you have transferability. So in terms of stability, well, this means that even if you have vibrations, if you have temperature changes or even shocks, people banging on the instrument, the performance should ideally be maintained and not changed during these things here. And when you're building optical mechanical things like a spectrometer, this basically translates into that you cannot have the optical components go out of placement, you can say, due to these vibrations or these influences. The transferability is a different thing, but transferability means that the instrument should give the same result if it's presented with the same sample. That may sound very simple and logical, but that's not necessarily easy to obtain, because the different spectrometers, the different instruments will have slightly variations in the tolerances of focal lengths, of all kinds of things that goes into an instrument, which means that many spectrometers will have a different peak shape or resolution when you look at different units. So why do we think Pebble is the right spectral sensor for this kind of things? Well, if we look at stability, first of all, like many other diode array spectrometers, the Pebble Neo doesn't have any moving parts. So that's the first thing. But another important thing is that we're using only transmission optics inside. So all the optics are lenses and transmission gratings, which is, if you I haven't time to go through that in this presentation, but if you investigate it, you will find that this actually is much less sensitive to angular deviations or vibration and things like that than if you're using reflective optics like mirrors, for instance. And the final thing is that there's actually no new thing about Pebble. It's proven technology. It's a way you build spectrometers for a long time, just the optomechanical components put into an aluminum frame. But of course, the new thing here is that we managed to make it so small. In terms of transferability, well, the Pebble Neo provides actually a quite good variation or low variation from unit to unit. And a lot of it is because we have made the design to be, you can say, tolerance tolerant, which means that even if you have variations in the focal lengths from unit to unit in the lenses, we have taken care of that or taken that into consideration. So we won't have a lot of influence from that. We inspect every single unit that goes out of our factory 100% to measure the key parameters. And key parameters are, as I mentioned, often things like peak shapes and resolution. And again, with the optical design we've done here, we have nice, clean peak shapes, which ensures a good unit-to-unit variation. That is not necessarily true if you work with mirror-based, spherical mirror-based systems where you have to go in off-axis. This can very often lead to odd-shaped peaks, which again is difficult to handle by software. Yes, I wasn't quite sure if we take questions now or we do it later, but at least that was the end of my talk. Thank you very much.
Thanks a lot, Thomas. Yes, that's a good moment for questions. So if any from the audience has any question to ask Thomas, you can raise your hand or you can add it in the chat, and we will transfer it to Thomas. But in the meantime, if people are thinking or want to warm up, I can ask a few questions. So you spoke about the resolution, if I remember correctly, it was 12 nanometers?
Yes.
Do you have any plans to go further in this resolution, and maybe you feel that there is reason also to go towards this direction?
Yeah, so it is going to be tricky to make even better resolution than that. So we actually have made two versions, so one with 12 and one with 16 nanometer. And what we've seen for many process applications, I mean, especially in pharma and things like that, Well, around 12 nanometer is good enough. I mean, it's always, of course, you think of resolution as a, you can say, a performance number that you want as low as possible. But in many applications, NIR spectra are actually not very sharp. They have a very smooth profiles. So often it's not actually the resolution that's a critical part. It has to be okay, but the number of pixels is often more important. So we may consider actually doing, let's say, a 256 pixel version if 128 pixels is not enough for the chemometrics model. So I think it's rather in that direction. Yeah.
I assume it's also kind of connected, no? So,
well, there's two things to the resolution. Of course, having more pixels, in principle, you would be able to get a better resolution. But I think when you are moving down to such small spectrometers, it's actually the optical system that sets the resolution. So even if you have 1,000 pixel, you wouldn't improve the resolution.
Okay, so what you're proposing that you can slightly increase the size and increase the resolution.
Absolutely. I mean, we have several other projects or products which is larger and which has many more pixels and also better resolution. So
okay.
Yeah.
I have a lot of questions, but let's pass to a question that comes from our audience, from Evclides Kuma from Unicab. Hello, Evclides. You can unmute yourself. Tell us a little bit what you're doing, where you're coming from, and ask your question, please.
Do you hear me?
We can hear you perfectly.
Okay, thank you. Hello, Thomas.
Hello.
Does the Ibsen technology used in the near infrared spectrometer have on longer lifespan than other technologies? The lifetime of the Ibsen spectrometer is longer than the competitors?
Well, I mean, I think it depends on the technology, but I mean, this is I mean, I think easily the lifetime is 25 years of this. I think most of our customers probably only require 15 or something like that. But yes, this is, I mean, as I mentioned, well-known technology. It's solid state detectors that's been around for many years. We have lots of products sitting out in demanding environments with the same type of in-gas sensors, and they've been out there for decades without failing. So we feel pretty confident that that this is very stable and has a long lifetime.
Okay, thank you, Thomas.
You're welcome.
Panos, you're muted.
Oh, I'm sorry. I'm really sorry. So I was telling that we have a comment also from Concom Spectroscopy Consultants, Richard Kronkober.
Okay.
Hello, Richard.
Yeah, I was just going to agree that in condensed phase near infrared, where you're doing molecular spectroscopy, the bands are very broad, and the extent of spectral coverage tends to be more important than a resolution better than around 10 nanometers. So I was agreeing with Thomas's comment that for those types of applications, looking at plastics and things like that, you don't really need any better resolution.
Okay, thank you.
Thank you, Richard.
I have one more question from Abundance Gerloop. What kind of communication do you use?
So first of all, we are an OEM supplier. So we are not supplying the complete instrument, but merely the spectrometer that is intended to be integrated into an instrument. So for that reason, we have basically I would say 3 levels of communication, starting from the most, what most people are used to is USB. So you can have a USB connection into your PC or whatever you want. And again, the software that you can work with there is just the raw spectra. So we are not providing the full chemometrics model or whatever to analyze data. We leave that to our customers to do that. But you can get the raw spectra out. You can control integration time and things like that over USB, or you can do it over SPI. The intention for that is as a more integrated device inside an instrument, where you may have a big motherboard with a microprocessor, and you want to talk to the spectrometer, to the lamp, maybe some shutters or whatever other things. So in that case, SPI is a good low-level communication protocol. And then the final thing we offer is actually that you can buy the spectrometer with direct access to the analog signal from the detector. So in that case, you have to build your own electronics. But if you're capable of doing that, that might be a good option for some customers also. So we actually offer 3 levels, you can say, of interface.
Okay, that sounds really good, because system integrators could use different ways of integrating your product into their components, no? Yeah. We don't have another question, but I really want to ask, because it was not clear from the picture. Do you have also the option for fiber connecting for light collection?
Yes. So there's actually 2 versions. There's a free space version, and there's a fiber connection version. So the okay. one with fiber will have an SMA connector. And if you look at the picture, maybe that's what tricked you. Right. The SMA connector is actually more or less the same size as the spectrometer.
Yeah. Plus you have 0.22 numerical aperture, no? So I suppose you're using the same for fiber, so not.
Yeah. Yeah, okay. So the idea is to overfill the NA, or at least fill the NA to get the best out of the spectrometer.
Okay, thanks a lot, Thomas. I do have more questions, but I suppose it's better to go to the next speaker.
Yeah, you can send to me afterwards. Thank you.
Good, thank you. And we can go to Maik Frede, the CEO of neoLASE, that they will present today the smart ultrashort pulse laser. Mike, whenever you're ready, you can share the screen, and the floor is yours.
Okay, so thank you for the nice introduction. Do you see my screen? Do you see my screen already?
Yes, perfect.
Oh yeah, okay, good. So my name is Maik Frede. I'm CEO of neoLASE, and today I want to talk about a new product which is called SMART, which is an ultra-short pulse laser system. So I want to give a few words about neoLASE. So neoLASE is one of the technological leader in the range of diatoms solid-state lasers. And in general, we are focusing on the industrial and customized laser system from single unit to volume productions. The application range is typically in industrial and scientific. So location is in Hanover, Germany. You see that on the right-hand side here. So we live in that nice green area. With other institutes like the Laser Center Hanover across the street, or other industrial industries. So let me say a few words about our products. So in general, neoLASE coming from laser amplifier development. So we started with laser amplifiers. Most prominent candidate here is gravitational wave detection. So actually all operating gravitational wave detectors in the world are equipped with neoLASE amplifier technology. And at one time, a customer came and asked us if we could combine their seed lasers, their oscillators, with our amplifiers to boost up the pulse energy of the laser system. And we start with, let's say, the first customized laser systems, or the first customized MOPA systems. Today, so we have a broad range of MOPA systems, which spans over from continuous wave single frequency lasers up to femtosecond pulse durations. So look a little bit inside the MOPA laser architecture for people who are not 100% familiar with that. MOPA stands for Master Oscillator Power Amplifiers. And so we buy and integrate oscillators from the market. So they are fully tested and fully integrated into our system, so that the user only gets one control interface for the laser. And then we amplify that into certain energy and power levels. For sure, we have further options for frequency conversion, pulse on demand, and other building blocks. So, and that allows us to offer a wide range of different pulse durations, repetition rate, and output power. We have that high reliable technology of our laser building blocks and the experience over the last years. So that it's like an industrial standard, even if it is a customized design. So a few words about the amplifier technology. That's one of the main building blocks here. So we have different laser materials, which are used typically in the 1 micron range for pico and femtosecond pulse duration ranges. So we can also do a frequency conversion to shorter wavelengths, which is typical second and third harmonic generation. But interesting here is that we are also working in the 2 micron range directly, which are new products which will be presented in the future. Nevertheless, so let's come to the SMART idea. So SMART was basically driven by the idea of having flexible laser pulses out of one system. And this is one of the main concepts here that what we want to show is selectable pulse duration. So we call it also open source technology because the source, the seed laser, can be plugged in and can be changed by the customer. And that's, I think, the basic idea here, that by selecting the source, the laser can be a nanosecond laser or a picosecond laser, or even a femtosecond laser. So it's simply by switching the oscillator as a seed source. And that gives the possibility of upgrading these laser systems. So a picosecond laser today could be a femtosecond laser tomorrow, without building or without buying a complete new laser system, and which also reduces the cost for sure. And this is one of the examples also of cost reduction or investment cost reduction, so that the laser is upgradable and you can change the laser parameters with your applications or with the growth into different directions. So we also offer, or the general idea is also a self-service architecture. So we have that 3 building blocks of electronics, seed laser, and the laser head. And the mechanical integrators will be taught to exchange these modules, so that it's a kind of self-service, which leads to a really high reliability and high uptimes of the laser systems. Let me give you some infos of the parameters. So a general application, I think, is a micromachining application like engraving, cutting, drilling. And we have different pulse durations which are selected typically due to the seed laser, which is connected. So here only a little range, I would say. In general, we have possibilities for other options and other pulse duration ranges, but these are some kind of typical parameters here. So if we look into the pico to nanosecond pulse duration range, we can use switched or modulated laser diodes, for example, which are in the range of 50 picoseconds to a few tenths of nanoseconds. So in the femto to picosecond laser range, we typically use mode-locked fiber oscillators with a few hundred femtoseconds down to a few 10 picoseconds. And with an additional pulse compression module, we can even go below 100 femtoseconds. So if we look into the energy and power levels, so it's a little bit related to the maximum peak power. So nanosecond pulses typically have a little bit higher energy levels. So here we are in the millijoule range. When we look into the pico to femtosecond laser range, it's about half a millijoule. And if we look into the femtosecond laser range, it's about a few hundred microjoules. So average power levels from a few 10 watts up to 100 watts. So that's pretty open. And due to the fact that we have that mode-locked fiber oscillators or gain switch laser diodes as seed lasers, so we can offer a single shot to a few tenths of megahertz pulse repetition rates. So and the basic idea also is you can see it here on the energies and pulse duration ranges. So you can have, for example, one seed laser which gives you a few nanoseconds and very high pulse energy for high material removal. And then you go switch over to a femtosecond laser pulse, for example, to do polishing, low material removal rate, but much nicer structure for some kind of polishing. Yeah, I think I want to quickly summarize. So neoLASE in general has the idea or provides industrial-proven laser technology, but individually tailored to the specific user application. And the general idea behind SMART is to cover that you can address different applications with only one laser by selecting different pulse durations. That the laser parameters are in general upgradable because you can switch over to different pulse durations. This is reduced of overall investment risk because you can further use your laser system because you can upgrade it into different pulse duration ranges. It has self-service use possibilities, and finally, it's sustainable use in laser technology. So yeah, thank you for your attention, and I'm pretty much open for questions.
Thanks a lot, Mike. Thank you. That was really nice to see that you can have in the same system different kind of pulses. You spoke about different pulse duration. I assume this one is discrete, correctly?
Yes. Yeah.
And just one more question. It was not clear to me if you can also tune the repetition rate.
Yes.
You can.
Yeah. So that's a typical way. So even with the mode-lock 5-molar oscillators, for sure you have a pulse picker, which gives you then single-shot applications and a few hundred kilohertz to megahertz. So that's all selectable. That's like, I would say, like the classical is a standard.
We also saw different kind of wavelengths due to second harmonic generation. You also have the possibility to have in the same laser system different outputs in different wavelengths.
Yeah, I think the wavelengths, what I showed here are the let's say the amplifier gain modules, which is related to the general amplifier gain material. So that's typically related to 1 and 2 micron laser ranges. But we also for sure do second harmonic generation or third harmonic generation, which then leads to green or a blue or UV output. And then this is possible in the same laser setup as well. So yeah.
Okay. I will continue with questions because I have a few, but if somebody from the audience would like to ask something, feel free. So the other question that I have is that, I mean, we saw that we can have different applications with this system. You let the steering optics afterwards on the side of your customer, or you can also deliver support into that.
Can you repeat? I didn't
mean, you have the laser, no, but you want some steering optics afterwards for whatever application. You also support them with this part, or it's up to the customer or to the other end?
I would say in general we support the combination. Also, we support because it's mentioned. So it's customized laser system. So we report mechanical applications or mechanical attachments, etc. But in general, the steering and everything else behind that is related to the integrator or to the user at the end. Yeah.
Okay, but you give all the freedom to customize your side.
That's right, and I think that's one of the key points here. So it's not a fixed system, so it's always free in different dimensions. So the inside are the general building blocks we're using all the time, but let's say the outer frame is very flexible and variable and can be addressed to different housing sizes, different additional applications. So connect whatever fiber coupling.
That's really nice to hear that you can also have room to shift around in terms of in terms of size. Sorry, and I would like to pass now to my colleague Antonio Raspo, who has a question for you.
Okay.
Yeah, maybe just a question or a clarification. This laser can be synchronized. I mean. Ramping and bus mode with application, how easy? I think that is possible, but
yeah, that's possible. So the electronics is related to an industrial standard electronic system. So we typically use, let's say, OPCOA as remote control interface. And the advantage for that control system is that they have all these kind of other remote interfaces. So it's like a terminal system. So you can integrate different control interfaces and you can program it and you're ready to go. So that's quite easy to integrate that into different interface architectures.
Okay, but this is made by programmable, in a programmable mode. It's not, let's say, in a real time, let's say connected to a robot or to a scanning head, just to have a real-time synchronization between the movements of the robots and the laser emission.
Okay, that can be done, for example, by simply the gating AOM, which is a classical part which is inside, which can address output power and can pick down the repetition rate. So interesting here is maybe the gain switch laser diode, which is even much more flexible. So we're using laser diodes for a few tenths of picosecond laser range. And the laser diode really follows the trigger input. So this is really, you can sweep the repetition rate continuously if you need, and can address that to your speed of your scanner or something like that.
Okay, thank you, Mike. And we have another question from a colleague of mine also, Tracy Vanek. Tracy, can you ask, please?
Hi, thank you so much, Panos. And,
hello,
and thank you, Maik, for the, sorry?
Just hello?
Okay.
Yeah,
hello.
Okay, good. Thanks for the great presentation. This is very interesting. But I had one question. So is the beam shaping, apart from your pulse duration, is the beam shaping, is that dependent upon the laser that you choose, or can you do anything? Are you limited on the type of lenses or beam shaping apparatus that is used with your system?
Maybe I'm not quite sure. Maybe I forspoke. Did I say temporal beam shaping or spatial beam shaping? I mentioned temporal.
Yeah, I was assuming temporal. So,
okay, good.
Yeah.
Okay,
but I wasn't sure if you had any, if you would support like special special lenses or any type of additional focus for a different beam shape.
Now, again, this is, let's say, one of these things we address is to the customer's need because it's customized, right?
Okay.
So it's not like that we have a standard go out beam diameters and or focus dimensions. So this is also something we do in cooperation with the customer, and he gives us a dimension or the specifications he needs, and we simply integrate the right telescope to fit to that parameters.
No, that's great. And to be able to vary the pulse repetition rate, that's incredible. So thank you so much. Appreciate it.
You're welcome.
Thank you, Tracy, for the question. Thanks a lot, Mike, for presenting and answering those questions. And I would like now to pass to the next speaker, which is Melvyn Collins from Micromachining, the Micromachining Sales Director at Oxford Lasers, presenting the ultrafar laser application for R&D to contract services. Melvyn, the floor is yours.
Okay, thank you. Share my screen. Click the share button.
There you go. Just full screen mode.
Just, we should be doing it now.
Perfect.
So thank you for that introduction. So my name's Melvyn Collins. I'm the Sales Director at Oxford Lasers. And what we'd like to do today is to share information on how we're moving ultra-fast laser micromachining from R&D into the contract services that we provide to our customers. So a little bit about Oxford Lasers, as is the norm. So Oxford Lasers was a spin-off from Oxford University, 1977. So that's over 40 years in the laser industry. That's making systems and now more focused on using laser tools. The nice thing, and I enjoy it, I've been with the company 3 years, and our original founder and his research assistant are still active within the business. So we have people who have served Oxford Lasers for over 40 years through the growth of that business. We've been laser micromachining in different guises since 1993 with different tools, starting back with copper vapor lasers. The broader offering that we do, we have two sort of major parts of the business. Both of those offer contract services and systems. We use lasers, and that's the purpose of this introduction is the laser system that we do. We provide tools and we provide contract services. The objective of Oxford Lasers is to make sure that we can offer the right tool for the right job. So we have over 12 different micromachining systems, different wavelengths, different pulse lengths, so we can do the right thing. We also offer imaging systems. Again, that grew out of the use of laser illumination. And from that, you provide tools which can do particle analysis, particle sizing. You can do grab images of inhaler sprays, etc. And all of that is provided, again, contract services, or we provide the tools. The specific part that I'll be introducing today is we have been using ultra-fast laser tools in R&D projects. These have primarily been either EU or UK government-funded projects. We've been developing new capabilities. What we're now doing is we've developed those capabilities into systems that we use in-house, and that enables us to provide contract services to our customers. So, for example, the project started with flexible circuits, and glass welding. We've now integrated those into, and the previous speaker talked about the integration. That's where Oxford Lasers comes in. It ensures that you can access those capabilities across there. So we have got multiple lasers, and those lasers provide us with the different wavelengths. We have different types of lasers which can give us both high and low pulse energy, different rep rates. Again, the focus there is in ensuring that we have the right laser for the job that is in hand. With this growth and development from the R&D projects that we have, we are now doing glass machining as examples. And again, previous speaker mentioned cutting foils. There are some new processes for processing metals, which using the ultra-fast environment can provide significant benefits to the customer, one of which is faster cutting speed, but you can also get reduced heat affected zones. So a little more detail now on the specific areas. So one of the tools, one of the projects we had was laser micro welding. There we were focused on welding transparent materials, primarily to metal, but we can weld transparent materials to transparent materials. The objective of the development project was for the replacement of adhesives. So you remove outgassing and potential movement during curing processes. And we're now applying that to specific applications. One of the really interesting things is our customers are not necessarily looking to just replace a process. They're looking to say, can they change design rules because you now have a new process with different parameters? So that is an opportunity to improve product offerings. As we know there, it's suitable for hermetic sealing applications. And just a few of the examples that you see there where we've been able to bond. Here is a lot of pictures of components where we've bonded different materials to a lot of stainless steel. The particular interest is we have demonstrated that we can bond material up to greater than 20 millimeters glass thickness. As you appreciate with lasers, the objective is to focus the energy to around the boundary condition, where the boundary is between those two. And we're able to do that through 20 millimeter thick material and still achieve the laser welding. Another area, and again, it grew from another different development project, was laser patterning. And one of the great advantages of ultra-fast lasers there is it opens up the selectivity across a much wider range of material combinations. So with these ultra-fast lasers, we can now selectively remove lots of different materials. we're able to, with the integration of the laser into suitable optics, we're able to achieve tracking gaps now down to single-digit microns with these materials, different material layers. The advantage that we're bringing to this with the ultrafast lasers is it reduces the thermal load, and that reduces the thermal load both into the film and into the substrate. So again, opening up opportunities for our customers. The again, one of the speakers mentioned about how these ultrafast lasers can be operated at different wavelengths, and that enables us again to ensure that you've got the right tool for the right job. The ultrafast lasers do also provide the ability for minimal film delamination. And a couple of pictures that you'll see there. One of the nice things, the patterning of the PZT there, it's not always straight lines. So lasers give you the advantage, as we know with beam steering, to enable to do different patterns of laser patterning, and in this case, laser removal. So the main purpose of this introduction was to say we're now bringing those tools to our contract services. What we do within Oxford Lasers is we take the laser from the OEM and we fully integrate that. So that system goes into a stable manufacturing tool. We're bringing that R&D knowledge that we've developed during the projects and now applying that to specific applications. So the tools that we provide, and the picture there shows an example of a high volume manufacturing tool that we produce. That's a class 1 laser. Across there, it has a class 4 laser internally. All of the software interface, the Scimitar tools, enable the user to gain access to all of that application capability. So we drive the laser through there, we drive the motion systems, we drive the control optics, all through a single interface, so that the user has access to that. In the case of the contract services, we are the user. So we use the tools that we have built, and those tools that we build, we can then offer, and we do supply those to our customers, and the customers are then benefiting from the knowledge that we've built up and the experience that we have in operating those tools within our own contract services facility. So thank you. That was a very short introduction to the expanding capability of Oxford Lasers contract services. So any questions?
Thanks a lot, Melvyn. That was a really nice presentation. Actually, the feeling I got is that you have full flexibility in wavelengths and fully customization to what your customer will need. Is that correct?
That is the main purpose, is to ensure, as I say, we use the right laser tool depending on the job that's needed. Rather than trying to make the process work with a different laser, we're trying to ensure that we have a very broad range of lasers such that we can use the right one that will optimize the application.
Okay, that's good. And just a question regarding all those ablation processes and the application that you have with your systems. You're using optical scanners or positioning stages for moving the samples around, or both?
We will use both. And
okay.
One of the things, the tool enables you to access both, either simultaneously or separately. Again, it will very much depend upon the application. If you want very high precision over a small area, then a galvo scanner is a good way to go. If you want larger parts, larger facilities, then using the XY motion is the right approach. So we do offer both, and again, that gives the objective is to ensure that the customer can get control.
Okay.
Use the best one for the job.
Okay, thank you. And there is one more question from Tracy.
Thank you, Panos. So thank you so much, Melvyn. This was very interesting. It was interesting to see that that you're now doing more contract services. So you have your precision micromachining platform, but you also have services now that you can offer that will also give you some interesting ways of developing new applications and new techniques. So it seems that your systems offer very precise control. I was wondering, Are you using a granite base? And also, how many attendees can you support?
We do use granite-based systems. One of the challenges, or some of the challenges that you have, are holding very high tolerances. Thermal management is an important part. We can and we do air condition inside some of our tools when the tolerances get very, very tight. We do go through to 5-axis tools. So many of the...
I'm sorry, I didn't hear that. What was that?
We can go up to 5-axis micromachining systems. Typically 3-axis is more common, but we have the capability to go up to 5-axis tools. Again, we use those tools internally. And it is one of the things that I really enjoy, that we have used them and we can use the benefit of that knowledge. And it is good because we do see many different types of jobs. And then we can deliver systems if required to people who have a much narrower range of requirements.
Very good. Thank you so much.
And there is one more question that comes from HGC class. Can you ask a question yourself?
Yeah, hi. Yeah, thanks for the introduction. Yes, for sure. So I have a question because you showed that you can actually weld the sapphire to stainless steel. It's quite interesting for me because usually for sapphire, the thermal expansion coefficient is quite high. So for normal laser processes, we have to do preheating of the glass to avoid the very high temperature gradient. So in this case, do you have to provide some preheating of the samples to avoid cracks also around the welding area?
And thank you for that question, Tree. And at the moment, we have not been doing that with that specific application, but it is something that, again, is possible and integrated within the systems. So for that particular task that we've shown there, we were not using preheating, but it is a process that we can apply to the laser welding process.
Okay, yeah, thank you for the answer.
So thanks a lot, Melvyn. That was really interesting, the presentation. And now I would like to go to our next speaker, which is actually Emmanuel Stratakis, the CEO of Biomimetic. And he will be presenting how they can develop laser systems that create anti-reflecting and anti-fogging ceramic coating. Whenever you're ready.
Hello, Panos. And thank you very much for the introduction and for the invitation to present our new product, the Biomimetics new product, that is, the first ever environmentally friendly glass with superior optical clarity, and this is the Thibault Biomimetic glass. This this glass is produced through a biomimetic texturing process that is uses only laser light, and this is a chemicals-free approach. And actually, the inspiration for the creation of this, for the production of this glass, is from nature. You can see here we mimic specific features, textures on the glass surface that are found on the surfaces of specific insects and butterflies, and you can see that the similarity is remarkable in texturing glass. And actually, this biomimetic texturing process is configured to minimize surface reflection while enhancing the transmissivity, and the surface reflection can be reduced down to less than 1%, and the transmissivity at the same time can go up to 98%. So the good news is that it is a single process, but we can treat practically any glass. You can see here some prominent examples, including fused silica, borosilicate glass, eagle glass, soda lime float glass. And in all cases, we have managed to reduce reflectivity that in most cases is down to 1% in most cases. And this is through a fully automated sieve and push button process. There is no new use of chemicals or consumables, as I mentioned before. And for small and medium scale applications, it's of pretty low cost. And depending, of course, on the customer needs, An obvious use case for this technology is optics, and you can see here different options for our customers. This is, for example, infused silica, depending on the spectral range, the visible or infrared, and depending also whether we need actually to have low reflectivity and increase transmissivity, or a single side treatment or double side treatment over the glass. So you can see here that we can also provide tunable haze for our glass specimens from 0.2 to 12.5. And please note here that the scattering resistance, that is an obvious question for this coatings, is low. Another elegant use case, I can say, and that take advantages of the powerful of laser processing, and also the simplicity of this approach, is treating the core of optical fibers with remarkable results, unprecedented results on the minimization of the losses during coupling, light coupling to optical fibers. Another very interesting version of Tetix glass is the Tetix anti-fogging glass that has been developed recently by Biomimetic. And this anti-fogging glass combines the anti-reflecting, the optical clarity, the superior optical clarity, with anti-fogging and super hydrophilic properties. And actually, this glass can be applied, can be used by our customers that would like optical clarity underwater or under humid conditions. And again, this is a green laser texturing process. It is a simple, and there is no need for chemicals or consumables, and can be a glass independent process. So thank you very much. Biomimetic is a spin-off company that has been recently established of the Foundation for Research and Technology, Hellas. And our motto is nature's ingenuity on surface engineering. Thank you very much for your attention. And questions, please.
Thanks a lot, Manuel. It's really nice to see that there down there in Greece, there are a few things nice going on. Huh? And I have a question, actually. You saw this fibers, no? And this anti-reflection in fibers, it's a big problem when it comes to stationary cavities, no? Connecting fiber connectors and everything. I was wondering, it would be nice to have such a treatment on a laser, on a fiber surface, but what about when it comes to cryocooling systems? Have you ever tried your systems there? To cryocooling temperatures? Yeah, somebody we can imagine that can avoid this one, you know, to connect those fibers to apply this one for quantum computing, for example.
I mean, the treatment is performed in ambient environment. So.
But its performance?
Sorry?
But its performance is preserved to different temperatures?
We have not tested this yet. We are very happy to see any, let's say, customers' needs so that we can test it. And we are open. We can provide this process to any, let's say, customer needs, including this cryo temperature.
Okay, this is really nice to hear. And there is one more question from Tracy. Hi, Tracy.
Yes, today I have a lot of questions, Manos. I'm sorry.
That's good. That's good. No problem. I'm happy.
So Emmanuel, very interesting what you're doing, but I'm not familiar with what the process would be if we weren't using your system and your lasers. So you mentioned that that there's no like chemicals and consumables that would be used in order to provide this type of treatment to the glass. What are those? I mean, what are you replacing here?
Nothing. I mean, we use no chemicals actually.
So I understand, but
the coating is itself, the texturing is itself on the surface of the glass.
I understand, but what would be the normal process using chemicals? What chemicals would be used?
Normally, the anti-reflection properties are realized by multiple layers on the top of glass coatings. And normally these coatings are CVD deposited, or let's say spin coated, or any other process that can deposit coatings from vapor onto the glass surface. So this is the competitive actually process.
So it sounds like your method would be faster as well as cleaner. Is that a fair assumption?
It's not faster compared, of course, to the chemical coatings process, because that's why I have mentioned that for the small and medium scale applications, the cost is low. But this is not the case, for example, for large scale applications where the coatings is, of course, is much lower. The cost there is much lower.
And could potential applications include eyeglasses and also space applications for large lenses?
We have all this in mind. We have, of course, for each market to do the figures, to place the figures down and see if this technology is viable. Of course, we are open to any, let's say, suggestion and any further, let's say, exploration of how this technology can be applied.
Very nice. Thank you very much.
Thank you.
Thanks a lot. We have a lot of questions, Manoli.
Pleasure.
Let's go with the first one. Comes from Maik Frede from neoLASE.
Yeah, I was wondering if you could comment on the damage threshold and deep UV wavelength ranges. I think that is something which might be interesting to use it within the laser system, like 200 to 300 nanometer wavelength range.
Okay, so the damage threshold, first, let's say, measurements we have is the damage threshold is expected to be pretty close to the plain fused silica.
Okay.
For the fused silica case, whereas for the deep UV, it's a very interesting spectral range, but with the equipment we have now, we cannot, let's say, present results on this spectral range. So it is an interesting spectral range, and anybody that is interested, please contact us in case that they can measure this, so that we can also have some numbers there. But our measurements start from 400 nanometers and above. So we don't have any information below.
But this is, if I got it correctly, this is due to your measurement technology. So you exactly. Cannot measure farther down.
Yeah. Okay. We don't have the capability to measure, yes.
Okay, yeah. Okay, thank you.
Thanks a lot. Now we can go to the next question, which comes from Alexander Newstad from Nodal Cars and Concepts.
Yes, thank you. You can hear me?
Yes.
Yes, we can hear you perfectly.
All right. Yes, just a quick question. We are a lighting tier 1 company producing for mainly automotive, motorhome, and defense. In automotive, we have usually polycarbonate outer lenses, which have chemical coatings from inside to boost anti-fogging and also anti-reflecting characteristics. But we also have sometimes modular headlamps with glass outer lenses, where they are also working as the secondary optics. Do you see application possibilities on glass optic lenses, for example, for automotive, with your kind of
yeah, it's obvious from my presentation. It's obvious that we are focusing on optics, and including these lenses that are used in the automotive applications, for sure.
Yeah, very interesting. I might reach out to you.
Yeah, this is great. We will do the connection later. I will send you an email so we can introduce to each other.
Sure.
This is good.
Thanks.
We're happy.
Yep.
And then we can go to the next question. It is from Trile Punk.
Hi, Emmanuel. Thanks for the presentation. It's very interesting. I have some questions. For example, for the anti-fogging applications, how much time it took for, let's say, 1 centimeter square area of the glass?
Now, for 1 centimeter square, we need, let's say, 3 seconds.
Okay.
To process this.
And the structure you create on the surface, could you estimate roughly the height of the structure? Like, are we talking about few micrometers?
Yeah, the height of the structure is about 150 to 200 nanometers.
Okay. Yeah. And also you mentioned that the field of view, I think, is 24 centimeters, right? Is it the field of view of the...
No, this is not the field of view, the maximum area, 25 by 25 centimeters that we can process with the equipment we have currently.
Okay. And one more question is, so Biomimetic is now like providing prototype for surface texturing, I guess.
Exactly.
Okay. Yep. Okay. Yeah, because it wasn't clear to me in the beginning. And may I know, for the green laser that you use, can you share? Is it like femtosecond lasers or is it nanosecond lasers?
It is short pulses. So you can use from picoseconds to femtoseconds. It's feasible to produce this kind of features.
Okay. Okay, perfect. Yeah, thank you very much.
Thank you.
Thanks a lot, Emmanuel. Florent, just one more question, then I'm coming to you. It's from optical sensing, Paolo Tagliabu.
Okay, thank you. I have a couple of questions indeed.
Okay.
I heard that the treatment can be applied on the surface of the connectors or of the fiber optics to reduce the reflectivity. And I'm wondering if it can resist to the physical contact of two connectors, for instance. Can it?
Yeah, the obvious, I mean, the obvious, let's say, purpose there is to reduce losses due to the coupling between the fibers, or the coupling of light from a laser or an optical source to the fiber.
Yeah, so no problem in the physical contact. It doesn't.
Yeah, this is, I mean, I have not presented the numbers there.
Okay.
Because this is underway. We are exploring the feasibility and what we can do on this. But I mean, the good news is that it works, but we have to solve all these questions before launching, let's say.
Okay. And another question, if I can. Another question, you mentioned anti-fogging treatment on glass. And can this be applied also to different materials such as polycarbonates or something similar, plastic material?
Yes and no. We have not yet explored, but now I mean, direct processing of polycarbonate or other types of polymeric materials, but what we are exploring is to use glass as a mold to transfer these features to other kinds of polymeric or soft materials.
Okay, thank you so much.
Thank you.
Thanks, Manoli, and thanks, Paolo, for the questions. And I would like to go quickly to the next speaker and thank him also for his patience because we were a bit late. Florent Thibault, the CEO of QiOVA. He will be presenting the multi-beam laser marking solutions. Florent?
Yes,
the floor and the attention of everybody goes to you.
So fine, let me share my screen. Hi everyone, thanks for still being online. Can you see my screen yet?
All is good.
We're good?
Perfect.
Excellent. So yes, thanks for all being here still. I'm Florent from QiOVA. And I want to talk today about very high throughput marking solutions, or laser marking solutions that are dedicated to the individual product traceability. Individual product traceability, I mean, is really a fantastic technique. There's a lot of value for the end users and for the industrials who are putting that in place. So the applications are spanning tracking and tracing, anti-counterfeiting, brand protection. You can get to all of this when you're putting codes, individual codes on your product. And I'm going to explain how we can help with this. So first, QiOVA, we're a French startup, soon a team of 10 people, specialized in laser application and the related technologies. And so we design and deliver very high throughput laser processing solutions for the industry with a specific focus on the multi-beam processing. So using several beams at the same time for processing. This is a technique we've been pioneering since 10 years when the company was founded. We have two main domains of application for this solution: laser marking, which I'm gonna focus on today, laser micromachining as well. And you can see the key sectors that are lux, industry, and medical. Essentially, we design tools so our customers are able to apply this to different sectors. In terms of capabilities, we have a very extensive laser application development capability in the lab. We have a lab in the factory in France near Lyon. We've been pioneering multi-beam shaping, and we have introduced the first product line, industrial beam shaping, dynamic beam shaping product line. I'm sorry for the automation. That was in 2015, and I'm talking today about the third generation of product that is integrated in solution, as we've been staffing up and consolidating our system integration capabilities last year with 1 million past fundraising we got in. So we got more capabilities and went up the value chain essentially to deliver this autonomous laser marking solution. So really what's specific with us, it's our mastering of the multi-beam laser technology. The idea is pretty simple. The industry always wants more throughput, and it's getting difficult to combine precision and throughput. So instead of using one beam and going always faster, why not using a lot of beam at the same time? And this is what we do with the Vulcan products. So the Vulcan, from the initial laser beam, it's generating 10 or 100 beam as you like. This is what you can see on the video on the top right. This is not a simulation, this is a camera capture. So you're generating beams as you need for the application. All these beams, they are independently controlled in position with a few 10 micron precision and in energy by the software, and you're applying them at the same time on the workpiece. So this is how you generate very significant throughput step-ups. Going back to the product, so we're releasing at Laser Munich the third generation of this dynamic beam shaping system that is called Vulcan. This is what you can see on the pictures. You have the beam shaping head here that is in red. You have the controller and coming with the software. In this OEM version, it's coming in an API software that you can embed in your existing software environment. And it's coming with an OEM strategy support that is designed to minimize any kind of downtime risk. And that is based on a hold swap, on-site hold swapping. So you can see we have two products essentially operating in the near infrared and in the visible range for the marking solution. So this product that we are the only one to provide worldwide are now integrating in the marking solutions. So the marking solutions are essentially based on standardized platform that involve a laser that is chosen for the application, thanks to the application development we can do in the lab. It's combined with the Vulcan product, of course, sometimes with a scanner when it's necessary, and I'll come back to that a little bit later. It's coming with the software, so you have the API, and you have also what we call laser digital tool. One of the power of a dynamic beam shaping approach is that you can configure the application with little programs that we call laser digital tool, and these ones are really specific for the application. And finally, the solution comes with all the software package, pre-sales, like application development, installation, training, and all the support along the product cycle. We have two really types of models of solution. It's based on two patented marking methods, very high throughput methods that I will present. One is called full stamp. The second one is called a pixel stamp. In the full stamp marking method, it's very easy. You can mark the whole code with one pulse. And this is what you can see on the camera on a video here. This is how you get a very differentiated performance. So you're marking a whole code in one pulse. So it's very easy to mark on the fly. You can do very small codes and you can get very high throughput, 1,000 codes per second if you like, if you're marking batch, or 10 to 20 unique codes per second for individual traceability. And really the key application domain is microcodes. This is a domain where the laser scanning is not very well performing. Well, as soon as you're below 3 millimeter, And this is really an area of comfort for the stem marking. You can see two examples here on copper, on Flex PC, typically. And two application cases very soon, very fast. So this one is in the pharma application. You want to mark this very small PVC straw. There are 2 millimeters in diameter, and you can see that we can mark more than 20 per second on the fly out of the extrusion system. And with this perfect quality that you can see here on the 500 micron code. You can read that on site with industrial vision as you like. Another example is related to anti-counterfeiting. This is a Swiss customer operating our product for 5 years now, where you can see that the customer is doing these small letters like this. So you have the scale here is 1 millimeter, and it's engraving, it's marking this Aztec code that is, it seems a little non-uniform, but it's in fact that you have an encryption key hidden in the distribution of small and large dots. So this is really to illustrate how easy it is to set up an anti-counterfeiting marking solution with this kind of very high precision. So we've seen the stem marking methods that is applying to microcode, serial, discrete traceability. Pixel stem marking, the limitation of the stem marking is that it's sometimes difficult to do large code on materials with a high marking threshold. So we've developed here the pixel stem marking, combining scanning and multi-beam, as you can see, where the idea is essentially here, if you want to do code, you're marking modules after modules. And you can see on a little video here how fast it goes. You need something like 100 milliseconds to mark one full code for 12 millimeter typically. So here again, you have access to 10 unique codes per second. And one of the really great features is that you can mark difficult materials like polymers, glass. And you see an illustration here, a direct marking on glass for pharma application without any micro cracks, 10 unique codes per second. And I will finish with this last example that is coming from the high-end wine liquors market, where the customers wanted to have a very nice looking QR code for direct interaction for the customer using this patented marking method. So we go 10 to 20 times faster than normal process. The appearance and the look, the touch is very smooth. So this is an approach that is very nicely fitted to very high-end branding here. And as in any other case, you can have a very easy reading using standard vision, you mean in a line, or in that case, you want to create a direct customer interaction. So it's important that you can do direct reading with a smartphone. That was short, but I mean, that's how it goes. Thanks a lot for your attention, and I'm happy to take any questions. Thank you.
Thanks a lot. Thanks a lot, Florent. That's really nice, but I still have a question. I'm sorry, maybe it's a naive question, but how do you create this multiple? How you program it? I mean, what's the technology behind it?
The base technology is based on special light modulator.
Okay, SNRS. Okay.
Essentially, and we've been pioneering the use of special light modulator to high energy applications. It used to be a lot used in holography or essentially low power, low energy. And since the creation of the company, we've been working on applying it to high energy. So it involves a lot of work on software and a lot of work on understanding mechanism like damage mechanism to be able to properly specify the operation range. And now more recently with the seed investors, the investors coming in, we've been pivoting to solution and integrating all of these capabilities, application, soft, hard, into this solution to more easily deliver value to the customer, essentially.
Okay, I understand. And I assume then the distance of the to be marked sample from your device, it's important, no? So do you have any real, no?
Yeah, of course. But I mean, we were all based on typical marking machine. So essentially, it's a different type of engine that you can integrate in existing environment, like a standalone machine in line. So we typically use 80 to 160 millimeter lens. I mean, this is what you typically use in a marking world. Yes.
Okay, and this optimization can be done easily, or you need somebody from QiOVA to do that from you?
You mean on site for a retrofit or application, yes, or for
or application of application?
Well, most of the time for the solution, we start with the lab. You know, customer asking, "Hey, I need to mark this at this speed." You go into the lab. You have a prototype solution. If it's interesting and we move forward, then we can simply propose design and manufacture.
Okay. So everybody in the room, that's really easy. Florent can do that for you.
Happy to take.
And then we can go to. Thank you, Florent. And we have one question from our audience that comes again from Alexander Stader.
Yes, Florent, thank you. Very interesting, very nice presentation. Again, as a lighting tier 1 automotive producer, we are always interested in traceability. Usually we have printing or PCB suppliers do, of course, some DMC codes on the PCBs. Our volumes are not that high that I think that this kind of mass production process that you are now showing especially would be interesting for traceability, but we also have on optical grade PMMA and PC lenses again, the need for texturing. Sometimes we don't go for micro optics, we go for specific textures, for example, for controlling glare. And here I would see opportunities with your process. If you say that you could imagine PC and PMMA optical grade to be used as a surface, often flat, because we speak about the in-coupling area where we apply the textures. Do you think that's possible to have some very specifically controlled features, yeah, lasered on this kind of surfaces?
Yes, I'm not sure. So if you like to print some very specific patterns on the surface, that's definitely something that would be done, and that would be done using this pixel stamp approach. Essentially, you're composing a pattern, full pattern from the individual pixels. So that would be applying the same technique to a slightly different application than the one I'm presenting. So yes.
Yeah, because currently we are using normal lasers and they go line by line, and this is quite a time-consuming process.
So I mean, that's very interesting because you're talking about the way we apply the technology in micromachining. It's about parallelization. Instead of using one beam, I'm using 10 and I go 10 times faster.
Exactly.
And that's that's definitely one of the application case that we use most likely in a micromachining, and that's something a topic I would be happy to discuss with Emmanuel from Biomimetic as well. Yes.
Yeah, I see some parallels here. Interesting. Thanks.
Well, thank you, Alexander. Bye.
Thanks a lot, Florent. Thanks. And do you have any other question? We do have another question, and that comes from Tracy.
Hey, Tracy.
So this was a great presentation, Florian. I really appreciated it. I love the dynamic beam shaping. And as a matter of fact, we have a technical report coming out on so many different techniques of beam shaping and possible applications. So this is wonderful and ideal. But what I wanted to ask you, so you showed a couple of security applications. So you showed the coins and you showed pharmaceutical bottles. And certainly, even within semiconductors, security for a semiconductor has been addressed with PUF, physically unclonable features. But what is the strangest security implementation that you've had to do or that you've encountered?
Oh, the strangest?
Yeah.
We've been asked once to look at parallelizing like a grilling process for how do you translate that? That's called hachis parmentier in French. That's a French dish that was produced industrially, and the instructors got to us, and they were a laser like grilling the top of the cheese, and they asked us to parallelize this. But unfortunately, we couldn't give a positive answer because the technology was not compliant. But that's likely the strangest one we've been asked so far.
That's amazing. This is just fascinating. I was amazed at how quickly you could put in a QR code. You could write a QR code. I mean,
could
just
do that in a few nanoseconds, really. And that makes a whole difference when you're tracing products that go online very fast. Already the key feature is this ability to do very, very small codes, very small codes. Yeah.
And then also applying this to microtexturing. So, normally we think of precision micromachining, which you can do as well, but applying the parallel approach to this.
Definitely. I've been focusing the presentation on the solution release. So that's what we do in marking. In the micromachining space, it's more complex. So we're essentially cooperating with people who have advanced laser processing, development capabilities. It's difficult for us to do that by ourselves in the lab. And then our contribution is to parallelize the process. So essentially to step up the throughput of the process. And the idea is to bring these processes that are always technically fantastic to the economical competitivity level so that industrials can finally integrate them and mass produce. Lots of these processes are really interesting, but stuck in a hole because of questions of economical competitiveness. Yes.
Yeah, no, absolutely. And being able to parallelize an application, say for a car body or for an airline chassis, I think would be very interesting. And by the way, we have another report coming out on precision micromachining, but not one. So,
maybe one last comment on this, on the interest of dynamic shaping versus, for instance, DOE, static beam shaping. The interest of dynamic beam shaping is, as in example you put, real life parts, they are 3D.
I'm sorry?
Real life industrial parts are 3D parts, complex parts. So in fact, you see the concept of having a lot of beam doing the same thing, but it's okay on a large surface, but you need to apply most of the time a several step process with very high speed on large flat surface or accessible. And then you need to process these little round corners or maybe fine tune stuff. And that's where it's really interesting to have a dynamic beam shaping because you can adapt the laser tool to the process steps. It's difficult always. Most of the time you don't have a plain square sheet. So having the same multiple beam is questionable in this case. So
I mean, just being able to take the beam and make a right angle turn and keep a sharp corner, it can be quite challenging.
Right. So laser is something you need the whole machine, and the dynamic capability is really interesting in processing this somehow complex part. And this is, by the way, a topic we'll be developing with the whole European consortium in a project that is called Operatic. We'll be starting this middle of the year. So you have the whole consortium looking at how to process surface texture at very high throughput, this kind of complex parts.
This is wonderful. We should speak later. Thank you so much.
Very happy.
You should. Thanks a lot, Florent, and nice to listen that there are solutions coming out from surface texturing. And I'm sorry that we're a little bit late, maybe not a little bit, but it was very nice. I really enjoyed it. I hope you do. And thanks again, the speakers. Thanks, the attendees. And all of you have a super nice evening. Thank you.
Thank you. Bye.
Thank you very much.
Thank you. Bye-bye.
Thank you. Bye-bye.
Thank you.